recording and share screen. Right, good morning. So we're changing tack in this course. So now I'm going to talk for a week or so to run us towards the end of this lecture series. So to begin with, I'm going to try and put a little bit of context. So I've been sitting there listening to Neil over the last few weeks, just like you have, and I'm seeing this like very broad, very abstract picture being painted, which has been really inspiring and exciting, because I've never worked as a data scientist. I've never worked a day in my life. I've been an academic my whole life. So I don't actually know how to solve a lot of these problems. Part of the problem where I come in, the stuff that I've worked, is when everything's already nice and set and done, and we can use it and do some math and we can predict something, right? But actually what we've talked about, what Neil's really talked about, is trying to set the whole scene of us coming to that point, right? So therefore, I come in now right in the end, and I'm going to try and just tie up the last few knots so that we get the whole pathway through it. So the things then that we've really talked about is these 3 A's, right? So the stuff, first things Neil's been talked about a lot was that how do we get to a setting where we actually combine lots of different data sources, how do we acquire data and so forth. So the assess state. And then the assess, like what are the things that we can think about and we have to think about, because we don't think about them, really bad stuff can happen. Right? What can we do with the data before what we actually know what we're going to answer? And then this is my part then. So saying that now you're in a setting where you have some data and you also have a question. Now, what can we do to actually answer that? And what do we need to think about when we actually try to answer that question? So I had a look of the program, of the whole course, right? And I try to roughly, and this is not a very good split, but I try to have a look at where your courses actually are, right? And this is especially true for this year, and for those you who might stay on for another year, it's even worse or worse. It's very, very skewed. There's an enormous amount of stuff on this part, right? There's a little bit of stuff here. You can argue if cloud computing should be there or not, but it's there. Over here, I don't even know, right? Can't really find much of that at all, right? Because a lot of the stuff here becomes very problem dependent, right? So now, why is that? Well, one of these things is that we're a university, right? And what we've been talking about data science as like this tool chain of actually solving real problems. And what universities really like to do, right, is to teach knowledge. When things are very specific, things are very clear, we figured out what stuff is, and then we can stand up here and talk about it. All the things that we've talked about have really been, it's a mess, right? And we've been trying to convey that notion of this is a mess and you somehow need to arrange yourself in this. There's been a lot more of things over the last lectures of saying you kind of have to think about this rather than saying you should really do this, right? You've been given a lot more warnings than saying how you overcome them, right? So that means that this is really hard to teach. We don't really want to teach this. And that's kind of what Neil's been trying to do over these last few lectures, actually saying, you have to think about this, but I'm not going to give you a clear solution to it. Right? You're going to figure out the solution once you do it. Okay, so another thing then is that when we then teach machine learning, which I've done for years, right, is that can we actually teach machine learning like this isolated concept that we usually do, where we say, cool, here's some data sets. You don't even need to think about where it comes from. You're supposed to do this. And then we can spend 10 weeks or 8 weeks just fiddling around with fun math, right? Can you actually do that, right? So now, maybe the thing is that you can't, right? Because one of these things that I heard from the lectures is that you need to put machine learning in the context of data and of humans. And if we don't do that, then we don't understand machine learning fully, right? Then we just become statistics, right? But machine learning is interested in something different. We're using statistical techniques, but we're fundamentally interested in something. So the plan then, see what I had on the next slide. The plan then of this part of the course is that we're going to roughly try and get to fill out the whole picture so that we get some machine learning techniques. But we're going to try and put machine learning in context of what we've done before. And maybe two parts or motivations of doing this course in this way has first been to make you good data scientists when you do, but also when you come and take all these cool courses I had on this address bit here in the end, that you can actually come into them with a context, right? Of saying, yeah, if I do that, this is what this means. And I really like that cool math that we're doing at the moment, but I have this in the back of my head, right? Cool. So when then do we need to do machine learning? Why do we do machine learning at all? So we have certain tasks which humans are very good at doing, like speech recognition, image understanding, but they're just too hard to program. We can't do this, right? So therefore, we use statistical methods. Or we can have methods which are, or things that are just beyond the capabilities that we can do as humans. It's just massive volumes of data, and it's something that we can't do. So these are the two things where I think machine learning comes in. So what machine learning then tries to do is that when we end up in a scenario where there's some form of knowledge gap, we try to bridge that knowledge gap by data. That's effectively what we do. So I like to think, some of you have seen this plot before because I like to use this plot. So I like to put machine learning into context using this. So let's assume that we have a setting, we have some problem where we can gather data. If you're at 100, that implies you've seen everything that's ever going to happen. Right? And then you have another setting here where you've got knowledge. And if you're at 100, you know everything. Right? So now on that line lies all the problems that you can solve with a combination of the two. Right? If you're down here, cool, you're not doing machine learning, you have a lookup table. If you're over here, well, then you know everything, there's nothing left to do, right? Machine learning is the setting where I don't have enough knowledge, but I have a bit of data, and I basically want to glue those two things together, right? So I'm not up there, I'm not up there, I'm somewhere in the middle of these two things. So I have these two disparate sources of knowledge, something which is very concrete and something where I have examples. And I want to glue them together. That's effectively what we do. Cool. So then, if you go to maybe some of my other courses, then someone will say, well, this is great because machine learning is exactly this thing of, as I said, bridging, putting knowledge into a learning system, mixing it with data. So that means we can just take these machine learning courses. We don't actually need to do all this stuff that we did before, right? And if you know, Carl will even say in courses, well, that's great. So I just have this mathematical object and I can parameterize my prior. That's where I put in all my knowledge. Cool. So that's fine, right? Everything comes into the machine learning framework and we don't even need to do this data science bit. But I think the biggest thing that we've been trying to convey, or Neil's been trying to convey, is that most knowledge is introduced before you do machine learning. Nearly always, right? Because these two stages that I had before contains an enormous, you're not just doing this randomly. You're doing this in a very, very, very careful manner. You're deciding to pick specific data sets because of something that you know. you're trying to prepare and treat the data. You think, oh, this might look like this. There might be noise of this form. I might do this. Maybe I'll put this in a specific database. I'll ignore this, back and forth, right? This is where most of the knowledge actually comes in. So on that graph, which I usually use to explain machine learning, just collecting data, all this processing that happened before moves you massively up the y-axis already. And we often ignore that. And what's even worse, we don't make systems of it, right? We do it and then we forget that we've even done it, right? Okay, cool. So that then would be the idea of these numbers that people talk about, the whole 80-20 part, right? Whatever it now is, but this is where an enormous amount of work happens, right? But we often ignore that. So what am I then going to do today? So I'm going to talk about what can machine learning actually do, and I'm going to try and structure and formalize the concept of machine learning a little bit. What role does then the data scientist play in this machine learning loop? And I'm going to try and put machine learning a little bit into context by being a bit more formal around this. So I'm going to do this by talking about statistical learning theory. So I'm going to do this just with the notion of trying to break this concept of what machine learning can actually do, because it's definitely not a magic wand that we can just wave around at things. So this here is a quote from Shah Ben David about what statistical learning or machine learning actually is, and what learning is. Learning is the process of converting experience into expertise or knowledge. I'm really happy that I don't have to teach AI, because then I would have had to start with a quote of what is intelligence. And like, learning is hard enough to figure out what it is. Intelligence, I have no idea. So let's just not aim for that, right? But maybe we can agree with this, right? So it's the aim of taking something that I experience into knowledge. So that means experience, we can probably think of what it is, it's data. And what we want to think about, what is knowledge in this case? How do we mathematically parameterize knowledge? So what people often do is then they start saying, okay, let's split up machine learning and look at it from different things. We can talk about supervised, unsupervised reinforcement learning, to start doing this. And then what people do after that is then they say, cool, let's look at methods. And then you find graphs. This one was something I found on the internet. Great, to go this, and then you take a course and you learn one of these after the other, right? Dum, 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 dum. And now you have a massive toolbox. You have really no idea where to put them and apply them to different things, because you've made machine learning like all these small tools, right? And that's it. And what I'm going to try and do is not do that at all. So I'm going to try and show what machine learning fundamentally is, and then we're going to, over the next few lectures, look at a very, very specific method. We're going to look at something called generalized linear models, which are incredibly powerful models, and that's the only thing that we're going to use, right? So we're not going to be in this case where we say, oh, let's just test 11 different models, see which one works best. I don't really know which one works best, and draw lots of conclusions which are quite possibly dangerous and false, right? Okay. So how can we think then formally about machine learning, what machine learning actually does? So let's start off by saying that we have a domain set. So I have a set of measurements and objects that I want to provide some label to. So we can think about classification, or we can think about regression in this case. So X is my input. And then I have a set of outputs, which are then the set of labels that I want to attribute to X. And then I have a training data set. I have a finite sequence of pairs in this product space X and Y. So this is what I have access to, okay? And then there is a probability distribution D, which governs these measurements. So this sits over the product space X and Y, okay? And then I have some form of data generation process. So this here is a mapping that goes from X to Y. So this is the underlying generating process that we're interested in recovering. Okay? And then our aim is to find some form of prediction rule that we will call H, and it's going to make sense why it's H, because we think about this as a hypothesis that maps from X to Y. And the ideal scenario is if H is equal to F. Right? That's the game we're playing. Okay. So now let's just simplify this even more, and let's just think about binary classification. This would generalize it. It makes life a little bit easier for us. So what we have here is that we got the data distribution, which is this blue and red stuff, the contour plots, right? So that's my P. Then I have a generating process, which is this line, F. And then I have some training data, S, which are these crosses. Right? And my aim now is to actually, by only taking these crosses, find this thing, right? That's the task, as simple as that, right? So, in order to do this, I need some form of measure of success, right? I need to have a notion that says, oh, I'm doing well at the moment. I'm doing badly. What am I actually looking for? So we can think about a measure that would be interesting. So if I would take here, so remember D is the data distribution. If I would take the set for a specific hypothesis H, I would take the set of points that are misclassified, effectively in this case, where H and F are not the same, and I would take the probability of that, right? That seems like a very good measure, right? If the probability of this is 0, well, I'm always right, right? If this is 1, I'm always wrong, right? So that would be something very, very sensible to aim for. And this is what we call the true risk. So would that make sense? It makes sense, but why is this not feasible? It's not feasible because we don't have D, right? If I had D, then, well, there might be other ways of solving this problem. If I actually know the data distribution. And secondly, I don't have F, right? So if I had F, well, there's nothing to learn, right? You know F, so job done, right? So we can't do this, right? If we could do this, machine learning wouldn't exist, right? There's nothing to do. We know everything. So what do we do instead? And this is what kind of would make sense, right? Is that you would say, well, I don't have D, but I got S. And S is this finite training set that I've been given. You gave me some examples to learn from. So what I can do instead, I can say that I don't know if these samples that you give me are really representative or not, but I'll probably trust you that you didn't try to fool me. Maybe you should not trust me, but you know, you're being used given this. So one thing that you can say, probably the most naive thing to say, is that you compute then what's called the empirical risk. So what you say is you count the set of points in your training data set where the hypothesis has a mismatch to the true label, right? And then you will take this. Fine, this is generally what we do, right? We get a performance on our training data and we try to maximize this. Okay. So what can go wrong if we do this? Well, lots of things can go very, very wrong. So let's pick. So this is just the traditional example that people give on this. Let me see if I can move this thing. Oh, the joy of having a... Oh, I use Emacs as a window manager. So floating windows is not really what it's happy about. But anyhow, so let's just do this. Let's just take the most stupid hypothesis that we can do. So I'm going to take the hypothesis that if you give me a label, a training data point, if I've seen this before, I'm going to take the label from the training data set. Otherwise, I'll just give it another label. I'll give it 0. Right? That's guaranteed to have 0 error on the training data, right? Now, if this was my distribution here, well, now, depending on which class I consider to be 0 from that one, I'm either going to have an error on binary classification that's 2/3 or 1/3, right? Make them 50-50, and you have a true risk that's chance, right? So you've effectively learned nothing, but you have a perfect training error, right? So this is the notion of overfitting, right? This is what we're trying to avoid doing. We're trying to design algorithms that avoids overfitting. Okay, so let's take and just think about how bad things can go. So I'll have this data set that I want to classify instead. Now, let's just say that I pick random subsets of this data. I find a classifier. On these ones, I find a classifier that's always nearly perfect. And then I compute the true risk of this. This here is the distribution of using this one. I think I used 80%. I trained on 20 and I classified on 80 to get the simulation of the true risk. And this one, 90 probably, right? So what you can see here is that sometimes on this one, here on the magenta one, I have basically a chance classifier, while it actually performs really, really well on the training data set. So what you have to consider is that the true risk that you evaluate is actually random, and it's random based on the training data set you pick. Right? So which training data set you pick is super, 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 super important. Right, so that's the first notion I want to get through. Okay, so the next thing is, how do you actually find this hypothesis? So even if I said, let's minimize or minimize this empirical loss, how do I even find that loss, right? I'm not guaranteed to find the optimum. I use some form of algorithm to find that. It might be a search algorithm, for example, right? I have some parameterization of my hypothesis, and then I search around in this space. But actually, the way this one should actually be written, really, the way we do it, is that I take an algorithm, apply it to the training data set I have, and I use that algorithm to search, right? So there's no guarantees whatsoever that I'll find the optimum, right? I don't actually know what I'll find. And as we've shown here, maybe it's not even good to find the optimum, right? So let's take this example here. That example there for this training data set had 0 error on the training data set. That magenta bit over here had also pretty much a 0 on the training data set. Maybe I would actually really want an algorithm that just doesn't find this one, even though it has a really, really good error on the training data set, because it's crap on the test data, right? So you can see how the search algorithm also has a massive impact on what we find, okay? Okay, so I'm just bringing up problems here. We'll get to some solutions eventually. Then, the next thing, so these hypotheses that we have, if we're using some search algorithm to search in this space of hypotheses, these hypotheses needs to be parameterized somehow. I can't parameterize every possible hypothesis. So I already have a limited set to search from, right? So I can just think about the hypothesis class that I can parameterize, right? So I have some capital H a set of possible solutions that I'm searching for this. So this then leads to these questions that anyone that applies machine learning needs to think about. So the first notion was used M here just because it fits with the book that I'm going to recommend. But how much data do I need to be able to say something? What is enough data? Right? Like, when should I stop collecting data? Data costs money to collect. Like, when should I stop? When can I actually draw a sensible conclusion from this? What is a well-sampled data set? I don't know. How much does my solution depend on what I can find? When I apply a search algorithm, how much can I say, well, this search algorithm will always find the optimal, so I don't have to take it into account, right? Just a test. If you've ever run gradient descent in SciPy or something, on something, you have a choice of about 12 algorithms that you can choose. Just change them, and you see that you'll get different results all the time on everything. Which one of this is best? I don't know. Right? This is a question. And then H, how much does my solution depend on the hypothesis class that I choose? Right. So now people study these things, and we're not going to go into this too much in detail, but I just wanted to give you a little bit of a flavor. So people do have formalized this, and there's a whole study around this which can be really exciting, and I'll give you a couple of references on this. So what people set up is something which is called PAC learning. That stands for probably approximately correct learning. So what they do is that they say, we will make an assumption that we are going to get a non-representative training data set with probability delta. Okay, so that means that if this is true, if my sample set is actually representative, then I can say 1 minus delta is the confidence I have in my prediction. Okay, so we're going to specify this. Then we're going to say the solutions that I'm looking for is the solutions so that whatever my empirical risk is, I want to guarantee that the true risk is smaller than epsilon. Okay? So now that means we're looking for hypotheses that are, I'll have to read this, that are probably with confidence 1 minus delta, approximately up to an error correct. Right? Now you've done a setting where you've added fluff in both of these places, right? You can never do this exactly. No way. You need to see all data and everything. But if you do this, you fluff things a little bit. Now you can start proving things about learning. Okay? Now, the first thing, I'm just going to give you a flavor of these things. Cool stuff that you can actually prove. And the reference there is for proving a thing like this. So what you can allow yourself to do is you can, for example, prove that if I pick a specific hypothesis class of a specific complexity, how much data do I need to provide this delta epsilon guarantee? This is really cool, right? So you can actually start saying something like, how much data do I need to follow? So there's lots of things around that in that literature. Okay, so now I wanted to try and bring another concept that we need to have in mind, and you might have heard this before. So let's say that.
So I have to interrupt. So Leslie Valiant, who developed PAC learning, was a key and won the Turing Award in 2010. So we just have to put these things in.
But always the Cambridge guy. I haven't been here for long enough.
Yeah, so he was, and he was in the same stairwell as Jeff Hinton was.
Oh.
So forget Turing, Leslie Valiant.
No. PAC learning is very cool. I just wanted you to, because sometimes, and the reason why people, to have some things against pattern learning towards the end of the lecture, but I just wanted to tell you that there is a theory of learning. Sometimes we just think about machine learning as these random things that we just try, right? And it can be really exciting to actually look at this and see. Yeah, cool. So I wanted to take another, introduce another notion which I think you've heard before. But let's say that we have a space of hypothesis that we're searching. It's this circle, right? So we limit ourselves. Let's say that these are all possible lines or something, right? Now I get some data, okay? Now it turns out that H star is the thing that's perfect on the true data distribution, right? So H star might lie outside of this, right? So it's outside our hypothesis. Then what I have is that I got H opt. This is the optimal hypothesis in my hypothesis space on the true data distribution. So that's the best thing I can ever do with this hypothesis space. Okay, then I got H hat opt, which is the optimal hypothesis on the training data. Okay, and then I got H hat, which is the thing that my learning algorithm finds. Okay, so now what we can do is we can break up an error. So the error that we're really looking at, right, that we're interested in, how good am I doing, is the error, this one to the optimal one, right? That's what we're interested in. But we can break this up into 3 different parts. So what we can say is that we can first have, see which order I've written them in. So we have the error between the thing that my algorithm finds and the optimal one that it should have found. This is basically the error that's introduced by picking A, right? By having a search algorithm that's not good enough. Okay? Then I have the error between the optimal one on the training data set and the optimal one on the true within the domain. That's effectively my estimation error. So what is introduced by getting a data set which is not representative. And then I got my error from the optimal one in the domain in my hypothesis rate out to the one that would be optimal. And that is the thing that's introduced by us limiting the hypothesis class. Right? And now what you can do is you can break down these errors, right, like this. And there is a concept which is often referred to as the bias complexity trade-off or the bias variance trade-off that people talk about a lot. And that is saying that if, I think I have a slide of that, if I place a huge complexity in my class, so I make this circle massively big, right? If I make that circle really, really big, I will have a low bias in the solution that I pick. So I would have a small error here, but I'll have a very high risk of overfitting, right? Now, if I can go the other way around, so I pick a very small, I pick only lines to classify, then I'll have a very large error here, potentially, but I'll have a low risk of overfitting. And these two things we often play around with, right? You've heard this before, I'm sure you have, but I just think this circle is quite useful to look at to be able to break down all the errors. And what the data scientist now is doing, what we're really doing when we apply machine learning, we need to put these into context, right? We really need to understand where the errors are actually coming up in this case, right? That's the notion. So just being able to see this, I think, hopefully, is a bit useful. Cool. So, another cool thing that people can show using a path learning framework, and this is a proof that I think if you're interested in this, you should really look at. So, if I would want to introduce bias in my learning algorithm, we said that, right? There is definitely bias on how it surfaces things. Is there such a notion that there's a universally good bias, so that one algorithm is naturally going to be good all the time? No, it feels like very unnatural, right? Because I'm adding a bias towards something that, say that I got some minima, turns out I always want this one, right? So it has a bias of finding one specific thing. But naturally, you can think of this as basically it's a zero-sum game. If you're good at something, so if you've got to win at something, you need to be bad at something else. And that kind of feels natural, and this is something which we call the no free lunch theorem. So the cool thing is, and I'm not going to go through this exactly, you can actually prove mathematically for a binary classifier exactly what the no free lunch theorem is. I just put this here, and there's a reference for going through the proof of that. It's kind of cool if you like these kind of things, but this is not what this course is about, but I just wanted to put it there for you. What it means is that there exists no universally good algorithm. It doesn't. For everything that something is good at, there is something which is also bad at. These are just equivalent. And then what it also means that every algorithm that does something useful does something based on some assumption. And some assumption is clearly also going to mean that it's bad at something. So it's quite natural, but I at least find it very cool that you can actually prove this and you can actually show numerical bounds on this, which is a bit mind-boggling, but very, very cool. Cool. So then, great. So Carl was supposed to talk about the excitement of machine learning, and the only thing he said is the machine learning is rubbish, right? So what we've shown so far is we can never have sufficient data. That's infeasible. We'll never find a method that will guarantee to find our solution, and then we can never be certain about the true risk of our outcome. So should we just give up then, right? That's effectively what I've ended up with, right? Machine learning is rubbish, okay? So if you want to know cool stuff about rubbish, here's a great book, the one I've referred to. It's free PDF on it. Here's a fantastic course if you want to know more about structuring learning around these things. So, machine learning is not rubbish. Machine learning is awesome. And if you look, take all the material that I've studied, and you can look at these bounds, you can look at all these things, and you see these are so far from reality as we shouldn't be able to do the things that we can do. That's basically what the math is saying. We're doing much, much better than we do. So there's this huge mismatch between what machine learning should be able to do and what it actually does, right? And the reason for that is this thing which I like to call like the difference between explicit and tacit knowledge. Everything that I've talked about so far has been like how to cook an omelette. Here's a recipe for exactly doing an omelette. This is explicit knowledge, right? We tried to make learning explicit, and we're so far off the capabilities that we can actually do. And then you got this thing, which is riding a bike. I ride bikes all the time. I have no idea how I ride a bike, and I can't explain it to you, right? That's tacit knowledge, right? And it turns out the machine learning that we do, why we succeed, is because most of it is down here. Most of machine learning is an art, and it's not a science, right? And I think there's a big fallacy, is that we think that the science, most of that art actually comes into these things we talked about before, right? How you actually set up the problem rather than fiddling with the algorithms. But what we often do is that we build a narrative afterward that all the value was added by the algorithm in the end. And that's really not true. So this gap then between what we can do and what we theoretically should be doing and what we're actually doing at the moment. To me, this comes into these points, right? So access, we introduce an enormous bias into what data we decide to acquire. When we assess things, the human bias into what you think we will do with the data, right? you probably have quite a good idea what we're going to exactly ask you about the final project. You know the data, right? You're human beings, right? There's certain questions that I'm pretty certain is not going to come up, and certain questions which are very clear that they will come up, right? So the last bit here is this curve fitting. That is if you do these jobs previously really well, that last bit is, again, just curve fitting. But curve fitting can be really fun. I built a career on curve fitting, and I think it's very exciting. And now when I've been negative the whole lecture, now we're going to wrap up a little bit and talk about curve fitting, because this can be really exciting. But it's really important to put that into context when you actually want to solve problems, right? The narrative that curve fitting is apparently AI is nonsense, right? Cool. So what we're going to do then is that I'm going to briefly introduce the types of models that we're going to talk about now, and then we're going to do them properly on Monday in more detail. These are the models that we're going to use throughout this. Then, because it's the end of the course and you have to submit this thing, I'm not going to introduce material the day before you submit your report, right? So I'm going to take the enjoyment of that, of just talking about a little bit of random stuff. But we're going to talk about unsupervised learning on Wednesday. And the notion of that is to get to visualization, which is a really, really important tool, and discovery mechanisms for this. The segue from then unsupervised learning is that we're going to see that unsupervised learning models becomes intractable. And when things are intractable, then I'm going to give a lecture on Friday on approximations and approximate inference. This lecture here, I hope you won't now all not turn up, but this lecture is just something that I wanted to tell you about, but clearly this is not going to be part of the course, right? It is too late, right? But I wanted to set the scene of a little bit for what you're going to do in the remainder of the courses during the degree. Cool. So then I'm overrunning, but I'll be a little bit quick, and I might go through these things again on Monday. So the models that we're going to look at is something called generalized linear models. So this here is us reducing our hypothesis set, our hypothesis class, to be very, very small. It's going to be a set of models that are linear in their parameters. The reason why we're doing this is the linear models is something that we can explain. It's quite natural to think about linearity. Okay, so what we're going to talk about this as statisticians. So this domain that we talked about before, we're going to refer to it as explanatory variables. Our output, we're going to refer to as our response variable. And our task is to find a hypothesis that explains our response using the explanatory variables, right? It's effectively it. So you have seen this, right? Linear regression. You've seen this tons of times, I'm sure. Linear regression is you set up like this, right? Oh, yes. And for those of you who downloaded the worksheet, my indices were all wrong in every place. There was a copy-paste going through the whole way. I'm fixing them. So what we do, right, is that we say that my response variable is a sum over the explanatory variables over each dimension, and I have a coefficient, beta, and then I add some Gaussian noise to this, right? Boom, that's linear regression. Job done. Nothing fancy about that. So because we have this noise, when we're looking for predictions, we are looking for the expected value. So if I take the expected value of yi given xi, it's very simple. I can split this expectation. I know the noise has an expected value of 0. So I end up with the expected value just being this linear predictor. Okay, we've all seen this before. Now, there is an equivalent way of thinking about linear regression. So it's introduced just as what we did before. Right? We say I have deterministic variables and then they've been corrupted by some form of noise process. Yeah, there's another way of thinking about it, and that would be saying, I'm just going to move the noise around, and then I'm going to put the noise inside the response variable. So now, it made no difference. What this means, though, semantically, is now you can think about the response being random, right? In the other case, the response is deterministic, but you can only determine it up to a specific level. Now what we're saying is that I have a response that's Gaussian. Okay? So now, if I would compute, or if I would write this, well, exactly what I wrote, if I would take this down and write that as how this is distributed, it's just as this Gaussian with the mean first moment being that, and the second moment just being the variance. So what generalized linear models do is that they generalize this concept, not surprisingly. What they say is that we have a linear predictor of the explanatory variables, that's that, and the linear predictors matches a function of the first moment of the response variable. Now you can see that it was confusing of me how to even explain this. So sometimes we think about it like this instead, and it makes a lot of sense. So what I have is that I have a linear predictor that I push through a function to get the first moment of that variable. That makes sense, right? Ish. So the components that we have is that we got G, which is called the link function. We have a response variable D that comes from a family of distribution called the exponential dispersion family. These are distributions which are parameterized by two variables. They have a location and they have a scale. So the Gaussian is one of them. Pretty much all distributions that you've heard of or ever used are part of this one. But so for the Gaussian, you have a mean and a variance, right? That's a location and a scale, right? So that's this. And then you have this linear predictor, and that's it, right? Now, it turns out that you can write a massive class of models using this. So I'm gonna skip this thing, but here is just a couple of models which I think you've probably seen. You've seen linear regression, you might have seen logistic, Poisson, log linear, ANOVA models. You might see next year if you take me and Neil's course. There's loads and loads of models like this, and because they're parameterized exactly in the same way, it actually gives you a really, really rich framework, and they're linear, so they're interpretable. You can say, oh, I use this much of this variable and this much of this variable. So we're going to talk much more about that next lecture. So here's then super brief and quick summary. So the take-home message for this is that machine learning might seem like it's the whole thing. It's not. It's part of the thing, and it's super important that you remember the whole tool chain. What we're going to do now is we're going to try and walk the whole way, but we're always going to think back to all these things the whole way, right? So stay critical, that's the key, right? And there is a theory for learning. The theory is not at all as good as what we're apparently doing. So there's lots of work needing to be done. So if you're keen on theory, on pack learning and things like that, there's lots of work to be done. And then use this idea of generalized linear models, but I didn't have enough time to talk about it properly. But the reason why we're using them is that they're explainable. Statisticians have used them for a very, very long time. So the literature is quite set and fine, and there's fantastic software to use for this. Cool. So we'll do this. Next lecture, Monday, generalized linear models. We'll do the lab again, the one that some of you started before. And then we have this lecture on unsupervised learning. That might be stuff that's interesting to you to try. Then we do the tick, and then we do this final lecture here on statistical inference. And that's just basically for me to try and give you some notion and set you up and confuse you and everything for the courses to be left. Yeah, cool. Thank you very much.
Quick announcement: if you don't have a MariaDB server, this is the stuff with AWS. I've set them all up now, and you'll get an email later today giving you a location of some MariaDB server. So if you answer the survey,